We've been talking about this environment, and as I sort of briefly mentioned before, each cell or each state has a expected value, and this expected value at the very first iteration, like when we initialize the value, its value is 0, and the same for all the other cells. And as also I kind of mentioned before, oops, the reward value, if it is not written like this, it's just going to be 0. So what we are talking about here is state value function, or just we'll just call it a value function for each state. And each state, or um, after each iteration, we're going to update the state's value function, and this is the update rule. So actually this is more like vt plus 1. So next value function of this state is defined like this, which is the expected value of next cell's reward value and next cell's expected value again. And then this is called discount factor. And it can be whatever number between 0 and 1 because it's more like decay rate or decay constant. And then at each cell, say your agent is here, and you have 4 possible directions. And each direction has a probability, like choosing. So we are choosing one of 4 directions, and probability of choosing one is we can just initialize it as 1 over 4. Then by 1 over 4 probability, we can choose one of these 4 directions. So all of a sudden, we can view this as probability, and the expected value of the neighbor cell is the random variable. So just like this, say your x, just a simple expected value calculation. Your x has 1 and 2, and your probability of x is say 0.5, and then expected value of x is 1 times 1 over 2 plus 2 times 1 over 2, and this is going to be 1.5. So just like this, what we're doing is calculating the expected value of next cell's value and the reward. So let's really do really simple example. Let me do this color. So at the very first iteration, I said your expected value was 0, and then we are trying to update this value after the 1 iteration. So your expected value of this cell as 1, 1 at t equals 1 is, so we have 1 over 4. This is, by the way, state transition probability, which is just the same thing as this. So given state, you choose an action. So given state, you choose an action. So let's start from moving up, and that is 1 over 4 times reward value of t plus 1. So if you choose to move up, the next state will be this cell, and then that is your possible next state. So real value of this cell as 0, 1 is 0 plus discount factor is just our constant. Then the state expected value function of this state is 0. And we finish it one first calculation, and then there's summation there. So we're gonna add moving the case of moving left, which is 1/4 again here, and then the reward value of the next state when we move left will be -1 plus discount factor, and then expected value is 0, and so on. And then obviously these are just empty cells, nothing's there, so it's gonna be L times 0 plus 0. And this is going to be, this is all 0, -0.25. So at time t equals 1, this cell's expected value will be -0.25. And that's the first iteration of this cell, and what we're going to do is just do the exactly same thing for every other cells using like a couple of for loops in coding. As the next, we can also view this this kind of like evaluating the state, not in terms of value function, but in terms of expected value of each action, and that is called just the Q function. So just to make it a little bit easier, let me talk about code first, like not actual code, but kind of mentality of the coding. So we're gonna have this one-dimensional array with 4 elements, and then say at 0 is the expected value of moving up, and at 1 that's the expected value of moving left, like that. And at array number 2, and that's the expected value of moving down. And the last one is obviously expected number of moving right. And that's it. So each state will have this kind of array, and what we are doing here is, instead of like calculating the probability of a state transition like this, let's just directly put the expected number to here instead of probability, and that's the idea of the Q function. And the same thing is, we are still evaluating the value function of each state. And then only difference is we are also putting calculating the expected value of each action and putting all these numbers to all these arrays. So let's look at this state. So we are still doing the same iteration. Say Q of say that's a policy, pi is the policy, so let's say let's only look at moving down. So, and that is 1/4 at the very first iteration, because it's all initialized as equally. And then the next state's reward value is 1 and 0.9, and then state expectation is 0, and that is going to be 0.25. So expected value of going down at this state will be 0.25. And then say let's look at moving left, and that is simply going to be 0 plus 0, 0. So the Q value of moving left will be 0, and for the same reason going up will be 0, and moving right is going to be 0 as well, because, well, it's just boundary there, so it's going to return no value, and then state will be of this cell itself. But in this case, if you move right, your state will be same. Your next state will be the same state, but in this case, in at the case of boundary, your value here will be not your current state's value, but oops, not the current state's value, but just to give it as 0. because it's boundary. It's kind of special case. And that's it. That's the very brief introduction about value function and Q function. And then there are two different algorithms using only value function, and another algorithm using only not only the Q function and value function together. So there are two different algorithms using these two concepts, and we'll talk about it.